Hello. In this video, following on from the last, we're going to take a look at solving the radial equation as part of solving spherically symmetric potentials. So the radial equation takes this form. We have the separation constant k squared over here, but we saw when solving the angular part that it's also natural to write k squared as L plus 1, just for historical reasons to do with the particular form of the solutions being the associated Legendre polynomials. So we can equally well write this in the following way, and it just depends on which branch of physics you come from as to whether you use k squared here or L plus 1. So they're just different choices of quantum number that you can use in this. We've gone for L, so we've labelled the functions R of R by the quantum number L here. A particularly convenient choice of solution to R of R is as follows. If we define some new function chi of R divided by R to be equal to R of R, we can rewrite the equation in the following form. So we can write it like this, where V effective of R is a potential defined as follows. The original potential plus h bar squared LL plus 1 over 2mr squared. And this term here is what's called the centrifugal barrier term. The convenience of writing this redefinition is that this equation up here is nothing other than our one-dimensional time-independent Schrödinger equation. It's just that we've had to redefine our potential to V effective. So putting everything back together, we get the ultimate solution to the problem. The radially symmetric Hamiltonian acting on phi Lm of x, the three-dimensional vector, is given by this, where the labels phi Lm have allowed us to rewrite the angular momentum squared operator as its eigenvalue h bar squared LL plus 1, acting on the eigenfunction. And the states phi Lm are defined as labelled by the quantum number L as a function of radius, multiplying the spherical harmonics YLM as a function of theta and phi. In terms of the normalization, we'd like the following condition. The integral across all of three-dimensional space of phi Lm of x modulus squared should equal 1. We get a choice as to how we distribute the normalization amongst the different parts, but a convenient choice to make is this. The integral of the radial part modulus squared across 0 to infinity of r is 1, where we've used the Jacobian of r squared, which just takes us from Cartesian coordinates to spherical polars. And for the angular part, this then must also equal 1. But we notice that this first term, the phi-dependent term, the modulus of e to the plus or minus im phi, where m is an integer, modulus square is always 1 anyway, so we just get the result as follows. So this is a particular choice of normalization we can make, which is particularly convenient. So in the next video, we'll take a look at a particular instance of a spherically symmetric potential, the hydrogen atom. Thank you for your time.